Thank you all for having me. I know I'm a last-minute fill-in. Super excited to be here. Super excited to talk about some research I did. I know I'm also standing between everyone and lunch and the bar opening, so I'll try to move this along. And so this will be similar to, I know we had some lightning talks yesterday, and I think Ava gave a lightning talk talking about machine bias. And so what I want to talk about is some research I had done. I had done research on social networks in school, and still I continue to do this, and I'm publishing a paper about it soon, about the detection of hate speech. And I want to talk about some data bias issues that I encountered and some of the lessons you can learn from that. And so some background on me. I mean, I work as a software engineer right now, work sort of as a machine learning engineer down in San Francisco, did a brief stint at Microsoft, and before that was in school, focusing on some CS research. And so everyone's already probably been here since Sunday, so you don't need me to tell you that machine learning finds patterns in data. And so when we're talking about machine bias, we're normally talking about a machine learning system finding the wrong patterns in data. And so an example is in an image recognition system to detect skin cancer. It may actually just be looking for patterns that photographs were taking in the doctor's office, not actually looking at something about the skin. And so that's an example of machine bias. I wanted to show one of my favorite examples, and you can find this blog post somewhere, but for a while, image recognition systems, whenever they saw these images of grassy fields, would always predict that there were sheep in the images. Because all the examples used to train, since sheep are always in these grassy fields, anything that has sort of the big and a lot of green, they just sort of assume it has sheep. And so this is the sort of bias that the training data wasn't completely representative, that it would always have this setting. And that goes into this nice image too. You know, I don't know if this is clear enough. Those aren't birds. And this is like the lightning talk yesterday, how they talked about adversarial examples. And these sort of biases can creep into the system. It can be a problem. And so this sheep example is pretty innocuous, but there's been much more serious and more immediately concerning examples in the news recently. I'm sure you may have seen some of these around Amazon's recruitment tool or some of the biases in criminal offender systems or in loan systems that end up biasing on account of race. And I think a lot of this may not come from people intentionally trying to put these biases into their machines, but being a little bit careless around the data and what sort of embedded biases are there. And so I think this is an interesting quote. And this gets into a lot of what I think the bias comes from, in that when you're working with data in the real world, it's always going to be messy, and there's always going to be some sampling bias or representation issues. And so it's really important to look closely at that. Because whatever machine learning models you make, even if you jump to really sophisticated models and you're using your CNNs and your impressive neural nets, they're only going to be as good as the data you put into it. These models, they are what they eat. And so it's really important to have solid data and to have a good understanding of what's going on in your data. So how did all this issue of bias come up for me? I've been doing research on social networks, and that led me into doing research on the detection of hate speech. My research was driven by what seems like a simple observation, that people share messages differently depending on what that message is. And so maybe a simple example is, if I had a secret, I might tell one person, and they'll tell one person, and that person would tell one person, and so on and so forth. But if I were sending an invitation, my message was an invitation to my birthday party, I might tell everyone I know about that. And so what I was researching, and this is along with a few other researchers, was the idea that with enough data and some interesting machine learning techniques, we could pick apart these subtle nuances in how messages are shared and use that to try to detect certain types of content. And so specifically, we started looking at how you can detect the spread of hate speech online. Most people do this actually through textual analysis is the most obvious way to do this. You look for certain slurs, you look for certain language. But one thing was interesting about looking about the sharing network too is that it might be able to give a robust signal And it's something that couldn't be reverse engineered. One of the big problems that Twitter had was that people had started using coded language to get around hate speech centers on the platform. But one of the things is that you can't control how the content is shared. And so this is why we started looking at this. And so as part of training our data, we needed a data set of hate speech examples. And that's where some of our bias crept in. And so at first, I won't get too deep into this, but a lot of the research was using what are called these graph kerneling functions, which are these graph similarity functions. And we'd use these to find similarities and the differences between different sharing networks on Twitter of how different messages spread. And so these are normally used in conjunction with support vector machines. Specifically, we found a lot of success using something called the Weisfeiler-Lehman kernel. That's probably a little bit wonky for right now, but if anyone's interested in obscure graph kerneling functions, we can chat. I'm your guy. And so through the first couple iterations, we had some okay results. The chart on the left is a heat map of different cascade and different sharing network sizes, with the smallest being in the bottom left and the largest being in the top right. And so we see sort of what you'd expect is we get richer cascades and richer networks. We're able to classify more accurately. We have this ROC curve, and we don't have a great result there. 0.72 isn't great, of course. For our experiments, we were doing it with highly imbalanced data, which makes this curve pretty hard to get to something like 0.9 or anywhere close to 1, just because we were at something like 95% sort of normal examples and what were supposed to be 5% hate speech. And so it becomes really hard to get this better. But we still were thinking, and I started looking through a lot of the examples that we had missed. And there were a few patterns that kept coming up. And the major pattern was that we were good at picking out a lot of certain types of hate speech, but especially gendered hate speech and hate speech concerning women, our classifier really struggled with and really couldn't pick up ever. And that was sort of surprising until you actually start looking through the data. You start looking for patterns and start trying to segment it in this way. And so that was a little surprising to us, mostly because we weren't the first people to actually be using this data set. There was a lot of hate speech research that used similar data. The data set used common definitions, so also they were having annotators use the same definitions that many other studies had shown, and we use this, a Cohen's kappa is a measure of the agreement between annotators. And it seems like all the people who we had look at these hate speech tweets and decide whether or not what label to give them, they all agreed on what these should be. But it turns out, even though they agreed, frankly, they were still probably wrong. And some of that is embedded bias within these labelers. But some of that is because it's also just a really difficult, it can be a really difficult boundary to delineate between offensive language and hate speech. And somewhere there's a gray area in there that can be really difficult and that we had a big problem with in our study. Of course, I found out this actually this paper came out just around the same time. It turns out this is actually a big problem for people in hate speech research, and that people had been struggling with this for a while. And so you can point to say that we just get new labelers and figure this out. But as I said, it's actually a pretty difficult problem. And getting good agreement and getting really accurate labels is tough. I think there was a quiz the New York Times did around what Facebook classifies as hate speech. And I think you can go look it up. It was a couple years ago. And so you can take this quiz, think about these 4 statements. You don't have to actually say it out, but whether or not you think this meets criteria for hate speech. And we don't have to talk about it too much, but the answers to this surprised me. And I think the line between offensive language and hate speech can seem sort of arbitrary sometimes for different people, and I think that was a huge problem we found with our labeling. And so what do you do at that point? I mean, for us, it was resampling. It was trying to get a sample of the data that was going to limit these sorts of biases and that would give a more representative training set for our model. And I think the other big part of it was just being forthright about what biases are in the model and what the limitations are. Even though we won't be able to correct, or we'll do our best, we may not be able to correct every issue with the model. We want to do our best to make that clear to people and to make sure people know what the limitations are and what problems we had. And so I just wanted to call out these three pieces as you think about bias in data and what to do about it. It's so important to have rigor in the collection and the management of training data and how you think about this data, to spend time analyzing and thinking about this data and the behavior of the models, especially on very different types of data or testing examples. And finally, this idea that, at the end of the day, you don't have to just do what the ML model says. I think it's completely false to say that AI is just math and numbers, so it can't be biased. But it's also completely false to say that machine learning is inherently biased. Machine learning is pretty dumb, and it just finds patterns in data. But what patterns it finds depends on the data you give it. And that data is up to us. And what you end up doing with the output of the model is also up to you. So I just wanted to run through that really quickly. Thank you so much for letting me get up here to speak. If anyone wants to talk after about any of this, I'm happy to. Thank you so much.